Yes, welcome. So transportation problem is has mainly two phases. There is what we call uh, the initial feasible solution. That's the first phase, and the second phase is optimization. So we want to look at just the first phase today. But even before we discuss maybe those phases of solving a transportation problem, we are going to do some bit of introduction on transportation problem, just understanding what a transportation problem is. We shall look at its layout, and then the various maybe types of transportation problems. We shall also have time and look at assumptions that a transportation problem has to adopt. And then we shall look at the process of solving a transportation problem, and this is where we are going to spend most of our time. So the first phase of solving a transportation problem will require that we find an initial basic feasible solution. That's what I've given the title of today's session. So that's what we want to look at today. And then maybe optimization of now a transportation problem. We shall look at some other time. So there are about 3 techniques under our initial basic feasible solution that we shall be using to determine in this session. And then optimization also has 2 more techniques, but we shall discuss them in the subsequent stages. So we just define what a transportation problem is. Yeah, transportation problem is looked at like an extension of a linear programming problem. For those who have done operational research, they look at transportation problem as also an optimization technique, just like linear programming, where you want to minimize the resources that you spend. Remember, linear programming was grounded on the fact that we're having scarce resources, but we still want to get the best outcome. But now in this case, in transportation problem, we are having goods that we want to transport from various sources to various destinations, subject, of course, to the supply and demand of the sources and destinations respectively. But we want to transport these goods from their sources to destination in such a way that we're able to minimize the costs that we use to transport the goods. So by goods here, we have just selected examples of goods. Could be oil, electricity, timber, and so on. Sources could be factories, warehouses, depots, and so on. And destinations could be, these are now the consumers, could be schools, could be supermarkets, could be stores, and so on. So basically, we are talking of 3 things. We are having goods, and these goods are being transported from sources to destinations. And so we want to minimize. So we are going to have several sources, maybe of transporting a particular good, and several destinations. So we want to minimize the cost of transporting these goods to the various destinations. And so a typical layout of a transportation table model will always appear like what you can see on my screen. So if I consider, let's say I have, let's say sources m of them. So I'm talking of, this is source 1, source 2, all the way to source m. So those are m sources. And then I'll have now destinations this end, which I may denote as D1, D2, Dn. So those are destinations. So when you look at the right-hand side, when I'm writing again here, this is actually what source 1 is able to supply from source 1, the number of units that source 1 is able to supply, the number of units that source 2 is able to supply, and the number of units that source m is able to supply. And what you see down here is D1, D2, D up to Dn. Now this is now the demand or the requirements for destination D1, the requirements for destination D2, the total requirements for demand, how many units those destinations actually need to be supplied with. Now you can see I have several cells. This first cell, when you see C11, C11 is simply the cost of transporting a unit of a commodity from source 1 to destination 1. That's source 1. That's C11. C12 is simply the cost of transporting a single unit from source 1 to destination 2. Then now this is the cost of transporting a single unit from source 1 to destination N, and so on and so on. So the Cs represents the cost per unit of a commodity or per unit of a product from a given source to a given destination. Now, you see also in the same cells I've written X11, X12, X1N. So these are now like units. Huh? So X11 could be units that have been assigned to destination D1 coming from source 1. X12, those are units from source 1 assigned to destination D2, and so on. So we shall have we can even from this particular transportation table, we can extract a matrix of C's only. You can see a cost matrix given as C12 all the way to C1N, and this is C21, C22, all the way to C2N, and this comes down here to CM1, CM2. This also runs all the way to CMN. So this is a cost matrix. You can extract a cost matrix from a transportation table layout. So we can also extract maybe the matrix of now just the units that are assigned in those particular cells. So sometimes typically you'll find that I may give you just a cost matrix of a transportation table. Like in this is what I've just been demonstrating there. And so that should not confuse you. You should just be able to know that this is the cost per unit of a product from source 1 to destination 1. And this is actually the cost per unit of product from source 3 to destination N. So that shouldn't confuse us when we extract matrices from those transportation tables. Now, upon knowing what now, knowing what a transportation problem is and the typical layout, we also now have to know the various types of transportation problems. So you'll encounter two kinds of transportation tables. And one could be where you'll find that when you sum what the sources are able to supply, the total supply here, when you sum, you find that is equal to what the demand from all the destinations is. So in a scenario where you get this row total equals to this column total, when the supply and the demand is equal, you get a common figure here. For example, you're having, let's say 40, 50, 100, 100, that is 290. And you also have maybe this is 90, this is 100. And then maybe you also have this is 50, 50. So that is also 290. So a scenario where the total supply and the total demand is equal, then that kind of transportation table is called a balanced one. So that's a balanced transportation table. But in the event that the total supply and the total demand therefore do not add up, then they not add up to the same figure, then we regard that transportation table as unbalanced. And maybe I say this from now, from this added that most of the techniques that we are going to be learning how to handle a transportation problem, right from the initial basic feasible solution as well as optimization, they all demand that before you address that problem, you make sure that you check whether the transportation table is actually balanced, so that if it's not balanced, then you find a way of balancing it before you proceed. And before we come to the end of the topic, we shall have seen how we can balance one that is unbalanced before carrying out, before solving it. Now we look at the assumptions. Most of these techniques in operational research, they have, before you use them, they must at least particular conditions as assumptions. that have to be taken into consideration. Now, for transportation problem, the assumptions are on supply, demand, quantities, the cost, and you're talking of also all numbers. So for supply, we are talking of there must be a maximum quantity which can be supplied from each source. Yes, each source you must be able to know how much each source is able to supply before we begin even applying this, so that we have a fixed figure that is a whole number. And then the demand, also each destination, there must be also a maximum quantity of units that is demanded or needs to be supplied with. And then the quantities, we are saying the quantities of supply available at each source and the quantities of demand at each destination are all constant for the period under consideration. Yes. So we are talking of the sources are not going to be changing figures, and also the destinations, they're not going to change the amount that they actually require. So the demands and the supply quantities are remaining constant for that period under consideration. And so even it is to the transportation cost. So we are saying the cost of transporting per unit of commodity, and sometimes it may not be cost. Sometimes that cost matrix, instead of giving you the cost, we may also give you profit for transporting maybe a single unit from one source to another destination. But that's on a rare occasion. So when you look at transportation problem, it's like it's majorly designed to minimize the cost of transporting goods from source to destination. So that means it's more of a minimization kind of, it has a minimization kind of objective in the end. But we are saying that cost matrix, the C's could be replaced by maybe looking at the profit you get by transporting a single unit from a source to a destination. So that I can have sources, yes, and I can have the total supply here. We're talking of these destinations, D1, maybe up to D3. And we are talking of, this is demand. So you're talking of, instead of having the C's, we could also be talking of maybe P11, P12, P13, and then maybe P21, and so on. So where P is now maybe the profit per unit of product from a particular source to a particular destination. So this could be now also profit you get. So, but that is a scenario, so that maybe now that transportation problem becomes a maximization where you want to maximize the profit you get. So, but again, I'm saying that's a rare scenario, and that scenario, should it occur, we always try to change that profit matrix into cost matrix. We shall also see how to convert that, so that we are then talking of converting a maximization problem into a minimization one, and for the major reason, so that we apply the techniques that we already have. Because the techniques we have, they assume that we are dealing with a minimization kind of problem. We are minimizing a transportation problem. So we do not have techniques for just doing maximization. So that means, should you be given a maximization problem where the matrix here is for profit and not the cost, we have to convert it again into to resemble the cost, so that then we apply these techniques so that it looks like we are minimizing the cost. When we are minimizing the cost, in other words, it's like maximizing profit. Anyway, then we have mentioned something on whole numbers, that all these quantities of demand and supply must be positive integers. They are positive integers. So back then, so that bit was just to give us a highlight of what transportation problem is all about. And so we now get to the big thing that we should be spending most of the time on here. And the first point, even before looking at the steps of solving a transportation problem, I've emphasized, I think I've said it, but it's no harm, that before solving a transportation problem, it is always important that you check whether the transportation table is balanced, And if it's not, then you balance it. And here I'm just explaining how you balance it. That's adding a dummy supply or a dummy demand if the total supply and demand are not equal respectively. It's not to worry on how you shall balance, because you shall have a practical example later on how to do it. But what is more important for us here is that for us to solve a transportation problem, we must know that that problem has to undergo two phases. The first phase is where you are determining an initial basic feasible solution. It's like a tentative solution you are getting first before you now optimize it. So that optimization, so the process of optimization, that's where you now get the best solution. So the first step is just determining the initial feasible solution. Then now you carry out optimization. So to get the basic initial feasible solution under transportation problem, there are three techniques that are used. There is what we call the northwest corner method or northwest corner rule. There is what we call the least cost cell method. And there is what we call the Vogel's approximation method. And these are their abbreviations. So famous known as VAM, and least cost cell is that. And most common ones, I think, are these two. I'll explain why this one is so special, and we shall be discussing it and coming to optimization. Because this Vogel approximation method can fall under determination of initial feasible solution, but it can also be help us find an optimum value to that transportation problem. Then later on, we shall then look at now what are the techniques of optimizing an initial feasible solution that we have obtained here. How do we now seek to reduce it further? That's now the process of optimization. So there are two techniques: the modified distribution method, famously known as MODI method, and there is the stepping stone method. So we want to look at, first of all, the first three. Then optimization will be a discussion on another day. I hope you're okay so far. Hello.
Yes,
Okay, thank you. So we can proceed. So the northwest corner rule. Yeah, so here we are assuming that at least you know the compass direction. You know, when you say northwest, this is south, this is west, and this is east. So that means when you're given that particular transportation table, you're beginning with the cell that is farthest on your upper left-hand side of the transportation table. And then you assign as many units to this cell as possible. But we are saying that the many units have to be the ones, you're checking the row total and column total. So you are assigning the smallest of it. We are going to look at an example. Introduce the row supply and column demand by the amount assigned to the cell. This literature sometimes appears tricky for the procedure. I would prefer that we do an example practically. Then, once somebody has understood the example practically, and be able even to construct the procedure by herself or by himself. So I wish that we draw this table at least where we are, so that when we do it together. So let me give you some 2 minutes. You draw the table first, then we can try to do it together so that you're also engaged as we do it and you don't get lost. So just 2 minutes, you draw the table. I'll be sharing the results, of course, on the notes, but just for now, also do some writing from the end. So draw the table, and then we see how we use the northwest corner method to determine the initial basic feasible solution. I hope the screen is big enough.
Yes, Marlene, it's okay.
Are we done?
Normally.
Should be okay now.
Yes, we are done. Yes.
All right. So when you look at this is a good example of a transportation table where, where you're having three sources, source one, source two, source three for a particular product. And you're having four destinations, A, B, C, and D. You can see source one can only be able to supply 300 units. Source two can only supply 400 units. Source three can only supply 500 units. When you look at these destinations, you can see destination A needs 250 units. Destination B needs 350. Destination C needs 400, and destination D requires 200. So we have said even before we begin the process of seeking to find the initial basic feasible solution, we check whether this is a balanced transportation problem or unbalanced. And by so doing, we just sum this. We get like the sum of the demand here, 250 plus 350 plus 400 plus 200. That gives us what value?
1200.
Yes?
1200. 1200.
200. And then we check the sum of the supply also, whether it adds to that.
200.
So it's also adding to 1200. So that means we are dealing with a balanced transportation problem, which is okay for us because if it's not balanced, we try to balance it first. So we want to see you have those destinations. This could be towns or so on. And you have these three sources where you can get this particular commodity that you want to supply. And maybe because these destinations are there, maybe are not at the same distance from the various sources, you have been given the cost, like the cost of transporting a single unit from source one to destination A is 3, it could be, let's say, 3 shillings, if shillings is the currency. And then the cost of transporting a single unit from destination one, from source one to destination B is 1 shilling. You can see it's even more expensive to transport a single unit from source one to destination C. Was this so 317426598332? That can give us a cost matrix where you just talk of now instead of C11, I'm now writing 3174, and then have 2659, then have 28332. So that will be a cost matrix for that matter, a matrix with 3 rows and 4 columns. But that's not the point or the reason for this part of the question. We want to see how we can, how many units will go to destination F from maybe source 1 or from source 2 and source 3. But eventually we want to have at least the minimum cost possible. So we begin from that procedure, the northwest corner method, the procedure I've tried to read and maybe doesn't make a lot of sense. So from this, northwest corner means that we look at the cell that is on the northwest coast, northwestern part of the table. So this is a table. This is a table. So this is what is more important for us. So if we are to draw a compass, the northwest corner cell is this corner on the far upper side of the left. So this is the cell that we want to allocate first. That's the cell that we want to allocate first for using the northwest corner method. So you draw a line under it. And now what we are checking to allocate how many units here, it is very easy. I was mentioning the row total and column total. Now these cells running horizontally are usually called rows. And of course you can talk of this is a column, this is a column, this is a column. So there are 4 columns and 3 rows. So you check like this particular cell that you have selected, the row total is 300 and the column total is 250. So you check between 250 and 350, which one is the smallest value? We all agree the value is 250. So that 250 is what we assign here. Once you have assigned 250 there, then it means when you look at destination A at the end of it all, it only required 250 units. So when you assign 250 in that particular cell, it means you have already met the requirement of destination A. So therefore you cancel 250 and you write 0. So if you have already met the requirement of destination A, it means destination A will not receive any other unit from source 2 and source 3. But then source 1, which has given, source 1 will then be at least be remaining with 50 more units to be supplied in another destination. Because when you look at this particular row, you have only given out 250. So it still has 50 more units that can be supplied to another destination. So you remain again with this new, you remain with column 2, column 3, column 4, and this other cell. So these remaining cells, again, the northwest corner one, is this particular one. Now, when you look at this again, you draw your other line. And then you now begin again comparing the row total. Now the row total now is 50, no longer 300. And you compare with 350. So 350 and 50, you see that the smallest of the two is actually 50. So the 50 is assigned here. And when you assign 50 here, it means destination B, you have only met part of its requirement. It still requires 300 more units to meet its demand. And then source 1 will now be depleted because it had the 50 has been assigned to destination B, so it's now depleted. So if it's depleted, it means destination C, we cannot expect destination C and D to get any other unit from source 1 because source 1 has already been depleted. Now you check the remaining again 2 rows. The one on the northwest corner is actually this one. Then you check its row total is 400. Against its column total 300. So between 300 and 400, you see that 300 is the smallest. So you assign 300 here. 300 is retail funding. So you assign 300 here. And this one now, destination B will have met its destination. Met its demand. And therefore you not again, assign any unit in that particular column. But then that particular source 2 will still be having 100 units to be supplied to either destination C or D, because source 2 has only given out 300. Now, you remain with these 4 cells again. So the one on the northwest corner is actually this. So you are checking 100, that's the row total against 400. The smallest is 100, that's what we are assigning here. So that now that means when you assign 100 there, you'll have depleted a source 2, but then destination C will still be requiring 300 more units to meet its demand. Now that means if you have depleted source 2, source destination D does not expect again a unit from source 2. So you remain with this last 2, and within these last 2, you cannot do anything much, because you can see so that destination C is still having 300 here. The 300 have to come here definitely, and these 200 have to just come here, because there's no any other to make this 500. So, I mean, this 200, then 0. Then this one will also be 0. So the last 2, you just go here. So that means you have ended up, you can see all these are zeros, all these are also zeros. So you have ended up all the sources, whatever they could supply, you have been able to supply, and you have met all the demands from the various destinations. Sorry, I don't know whether there was a question from somebody. Are we fine up to that stage?
Yes, Mwalim.
Yes, Mwalim.
Thank you. Yes, you're good students. Thank you. So that means now, for us now to find an initial basic feasible solution, which is actually cost. This initial basic feasible solution is actually determining the cost, the initial cost that we can use to transport. Remember, let me use different color. When you look at cell 1, the cost of transporting a single unit from source 1 to destination A is, let's say I was using shilling cells, for example, 3 shillings, and you have assigned 250 units. So the 250 units will now require how much? 250 times the cost of transporting per unit. So that will be the total cost of transporting a unit from source 1 to destination A. Plus the cost now in destination, in this particular, this cost here will now be given by 50 times 1, plus this other cost here will be given by 300 times 6, plus this cost here will be 100 times 5. This cost here will be 300 times 3. And then this other one here will be 200 times 2. How much do we get? We sum that. So 250 times 3, 50 times 1 is 300. You get what?
$4,400.
4,400.
Yes.
Thank you. So I think that also confirms with what I also have. Yeah, so that is the initial basic feasible solution. So we are saying the units assigned, I've just picked out those cells, so that the total cost is what you have just done to get 4,400. So that is now like a tentative, but roughly you require 4,400 to transport goods from the 3 sources to the 4 destinations, so that you are able to meet the demands of the 4 destinations, and you're also able to actually supply all the units that the sources are able to offer. And so what you'll be doing now in the second stage of optimization, you'll be trying to check whether this is the maximum possible amount you can spend, or there is a way you can do the reassignment so that you maybe have a reduced figure that you can spend again to be able to meet the demands from the destinations, and also be able to supply all the units that the sources can be able to supply. So that is what you'll be now trying to check in optimization, trying to do iteration, kind of, so that you get the best possible figure, if this is not actually the best. So that is what we have under least cost cell method, northwest corner rule. So that we are saying, starting with the upper left hand of the transportation table, assign as many into this cell, but the amount assigned is a smaller of the raw supply available or the column demand requirement. Then reduce the raw supply and column demand by the amount assigned. If the raw supply is now 0, move down. So those are the stories. I think it's better understood practically, like what we have done. But nevertheless, you can also read through the steps. So that's how we do find the initial basic feasible solution using northwest corner method. So I want us now to look at the second approach, which is fairly similar, the least cost cell method. The least cost cell method. And again, I think you'll just draw the same table again on a new page so that as we discuss, it becomes easier. So just draw the same table first before we look at it. I'm using the same example. You can begin.
Yes.
Yes, madam.
Yes, now the least cost cell method, just as the name suggests, you are saying we are looking at the cell first of all with the minimum cost of transporting a unit of a product from a source to a destination. So that's what you are looking at. You identify among all the cells which one requires the least or the minimum cost of transporting a single unit. And you're saying that the lower cost cells are chosen over the higher cost. It's like an echo. I don't know whether you're experiencing it from your end. So you're saying the lower cost cells are chosen over the higher cost, and the objective is to have the least cost cell of transportation. Remember, we want to minimize the cost of transportation, and so the least cost cell, as somebody is thinking of, let me begin first of all, like supplying units to the maybe destinations that I spend less in transporting maybe goods to those destinations first. The kind of approach. So the steps, the first step, identify the cell with the least cost, then allocate the maximum feasible quantity, eliminate the row and column where allocation is made, and repeat the steps. I think which are the key important step is just to identify the least cost cell. I mean the cell with the least cost, and then just do the allocation by comparing the row and column total, like what you have just done under the northwest corner approach. So that when you look at in this entire cell, you'll agree with me that the cell with the least cost of transporting a single unit from a source to a destination is this particular cell. Because you require only one shilling for if they're in shillings to transport from source 1 to destination B. So once I've identified that cell, I check its row total against the column total, and again, the list is 300. So you assign 300 here, and therefore this will be 0. And that means that I'll have a depleted source 1. So source 1, there's no way it will supply units again to any of the other destinations. But then you'll agree with me that destination B will still be requiring 50 more units. Will still be requiring 50 more units to be able to meet its demand. Now, after I've done those cancellations, I check now the remaining cells again. Which one has the least cost? You'll agree with me, is either this cell or that last one, because they already have 2. At this stage, I'll say just pick any at random. Pick any at random. But for now, for demonstration, let's all of us pick this one. Let's all of us pick this one. I'll make a comment after that. So let's all of us pick this 2. So if you pick this, then it means I compare the row total against the column total. I'll assign 250 units here, and I'll have made the demand of destination A. But then source 2 will still be remaining with 150 more units to be supplied to any other destination, and therefore we remain with 6 cells that also require units to be assigned. The remaining one, again, now that means we shall come to this other second 2, because the remaining ones 2 is still the smallest. So you compare 200 and 500, you will have to assign 200 here so that you meet the demand of destination D. But then source 3 will still be remaining with 300 more units to be supplied. Now, once you do that, you're now remaining with 4. Again, 4, you see you have 3, 3. We again pick random, because those 3 are the ones with the lowest. So if I pick this one, you'll be comparing 300 against 400. So that means you'll assign 300 here, and that way you'll have made the, you'll have depleted now source 3, but then destination C will still be remaining with 100 more units to be supplied. Now, when you check column 3, column 3 has only now this 100, which has, and one cell which is unfilled. So this 100 will just go there, even if I was, and this column B has only 50 units at the end of it all. They'll just come here because only one cell blank. But still you can compare for 6 and 5. 5 is still the smallest. And so I'll be comparing 100 and 150. You still have 100 and this will be done. And this will remain 50. So that this 50 is what comes here. And you'll be done with this. You'll be done with the other one. So that's how you do assignment of units using the least cost cell. The approach is just the same as the northwest corner method, is only that the cell you begin with is for least cost cell now requires that you identify a cell that has the least cost. So just like the previous stage now, we calculate now the initial basic feasible solution by now having 2 times 250 plus 1 times 300 plus 6 times 50 plus 5 times 100 plus 3 times 300 and plus 2 times 200. 2 times 200. And you get that particular figure. You get that particular figure. What you are getting from the end.
$2,900.
Yes?
$2,900.
900. Huh? The silence of the other side. I want to presume that is the correct position. I want to make this clearer. In scenarios where we have now some cells, particularly when you're using the least cost cell method, when you have some cells having maybe same values of the costs, somebody who has chosen this cell first may get a different value from the other one who has chosen the other one. There is a likelihood that they may end up with a different total value of the initial basic feasible solution. And so that one doesn't have to worry you as long as the procedure is okay. However, during optimization, when they're now doing optimization, the second phase of that transportation problem, because most of the time transportation problems we may not be stopping at the least cost cell. We may be demanding that you optimize it. You'll find that during optimization, the two fellows who have found different values as the initial basic feasible solution using the same technique, they will arrive at the same figure during optimization. During optimization, they will arrive at the same figure. But I'm saying this is only working for least cost cell method, because if it is the other techniques like the VAM method and the northwest corner, there's no way the initial basic feasible solution will be different. They'll always have the same initial basic feasible solution and the same optimal solution, even if we have cells that have cells that share actually the same cost value per unit of a product. But under this cost cell, there is a likelihood of even having variation in the solutions of the basic initial feasible solution. So that should not be a worry. Like for me, I think I have 2850 here. And I think 2850 was coming as a result of, I think I started with one and the other. So that let's just assign so that people can see this difference that can happen. So that make it more clearer. So maybe you all just observe my screen so that we do it here together. For now, this is a second scenario. Suppose we are beginning with this. This one I had assigned 300. So this was remaining 50. This was now nil. And therefore, we are not assigning here. Then I came this as the second one, which I had assigned 250. Then, so that means I was done with this. This remain 150. So I came here, I assigned 200. This became 0. This became 300. Now, suppose now I begin with this 3, because I think the other time I began with the other 3. So let me begin with this 3. So I'll be assigning here 50, so that I'm able to meet the demand of destination B. Therefore, I'm not assigning anything here. But this one will be remaining 250 now. Now, when I come here, which is 3, so I'll be assigning 250 here. Then, so that I'm able to deplete. So it's 3. And now destination still be remaining 150. So that now this C will now have 150. So that this is now done. This is now done. So that can also be an approach. We have now begun with another cell of 3, 0 of the other one. So I think this is what I had used. So that now I'm talking of 300 times 1 plus 250 times 2 plus 5, 150 times 150 of 150 times 50 plus 50 times 3 plus 50 times 3 plus 200 times 2. Let's confirm that figure kindly.
It's 2850.
It's 2850, yeah?
Yes.
Yeah, so I think so that's still true. That's still okay. But you'll find that somebody with 2850, another one 2900, when they'll do the optimization, they'll all arrive at the same figure. So that is the point I wanted to emphasize. That at least cosine method is able to yield sometimes different solutions for the same problem. And when you're doing the basic initial feasible solution. Thank you. Can we now look at the last method under determination of basic initial feasible solution? And this is VAM method. VAM method. So it's the same question I'm using again. The same question. I'm going to give you the procedure there, but I want us to add some more columns now. This one involves a lot of drawing. So what I want us to do is to add some more columns. Let me see if I have a table or something. Yeah, let's have something like this. This is a table that we have for transportation. Then I've added some 4 more columns this side, and also some 4 more rows below. I've called this column differences. Those are row differences. So just add some more. We draw this table so that we use it now to do the VAM method. Are we through?
Yes.
No, normally, a few 1 minute. Okay, madam.
Ndembe handi aise novereri pamareva tamasayo sikira hakanyasaya panga.
So we are looking at the VAM method, or what VAM stands for, Vogel's approximation method. It has a number of steps here. Here now we have created some rows and columns. So we compute what they call the VAM method calls penalty cost. And this penalty cost is simply the difference between the unit cost on the second best route in the row or column and the best route in the row or column. Maybe we do that step first so that we are able to understand what that means. So under Vogel approximation method, when you look at the first row, the best route is one that you spend less to transport goods from a source to a destination. So if I'm looking at row 1 and I'm looking at this first cell, I spent 3, this one I need 1, this I need 7, this one 4. The best route is this one of 1 because I spent less. And the second best will now be this one that I spent 3. The third best is the one I spent 4. And the fourth best, or the last one, the worst, is the one I spent 7. So when you're talking of now identifying, getting the difference, which they are calling the penalty cost, is now getting the difference between the best and the second best. So in this first row is 3 minus 1. And that's what we are writing here as 2. So that will be the penalty cost there. When you check the second row, the best root is this one where you are spending 2. And the second best is 5. The difference is 5 minus 2 is 3. So what will be the row difference for row 3? Row 3 will be what? 1. That's correct.
1.
Now we do the same to the columns as well. When we look at now column A, the best root is this one where you're spending 2, and the second best is 3. So the difference is 1. So that's a column difference. And then we check column B, it will be 2. Then column 3 will be 3 and 5, 2. That's 2. And then this is also 2. We okay up to there?
Yes.
Yes, so that is what we shall be doing almost across all rows. So that's what we are calling the difference between the unit cost on the second best root, either in the row or column, and the best root in the row or column. Then now the second step is identify the row or column with the highest penalty and assign as many units as possible to the best cell or root in the identified row or column. As many units as possible to the best root. So let's go. And first of all, now we are looking at this as now we are now looking at this. Just a minute. Okay. Now we are looking at this column difference and draw all this as one thing. I can use a highlighter. So we are looking at all this as one set. As one set, we are checking which one is the highest value. That's the highest penalty cost. We check. So we can see all of us that the highest is this value 3. Isn't it? 3 is the highest. And so if 3 is the highest, what we do is that we check 3 is now corresponds to this particular row. So in this particular row, we check the best cell in this row. And the best cell in that row is actually this cell with 2 as the cost. And so we assign as many units as we can to this particular cell. So this cell again, now we have identified, you check the row total and the column total, 400 against 250. 400 against 250. So you'll see you'll assign 250 here. And then this one remain with 150. But this one will be done. So you'll be done with this particular destination A. But then source 2, you'll still be having 150 units. So you're done with the first iteration. So we go to the second iteration again. We begin calculating the row total and column total. We have now eliminated column A. We shall no longer need it. So we shall just use a dash because we are not going to calculate the difference. We are done away with it. Now, column B, the difference again going to be 3 and 1 is 2. Column C is going to be 2. Column D is still going to be 2. Row 1 is now 1 and 4. So it's 3.
How do you get 2, 3, 1, 1, 2, 2? Kindly repeat.
No, don't worry. Let me repeat this second one that we are doing. Utaelewa tu sijali. It can confuse somebody. Or let me repeat the entire question anyway. There's no harm. So I was saying this, that we are identifying the best root in each row. and the second best root in each row. And you also identify the best root in each column and the second best root in each column, or rather the destination. And so we are using, because this is a cost matrix, we are looking at a cell with a cell that requires, or a destination that requires the least amount of money to transport a single unit of commodity from one source to a destination is what it makes that cell to be the best. So that when you look at the row 1, the best cell is this one, where you require 1. The second one is this. So that now, in this particular case, the difference between the 1 and 3 is 2. When you come to the second set of cells, the best root is this one of 2. The second one is 5, second best. So the difference is 3. When you look at the third set of cells, the best root is 2, and the second best is actually a tie, is 3. So the difference between 2 and 3 is 1. Then we now come to columns. We now look at cells column-wise. We look at cells column-wise. We are now looking at this particular set. The best one is this, the second best is that, the difference is 1. When you look at this, the best is 1, the second best is 3, the difference is 2. When you look at this, the best is 3, the second best is 5, so the difference is 2. And so it is, so the difference is 2. So that's how we are getting those values. Now, once you have gotten that, we are now checking. We have said that the first column and the first column difference and the first row difference, we are treating all these units as just elements of one set. So we check which one is the smallest of all. I mean the biggest, sorry. So the highest of all from this, we have said is value 3. And so that means once you have identified is 3, we check the row or the column, the row corresponding to that, or the column if that value had been found made by the lower end. So in this case, we check the best cell in this particular row. We check the best cell now in this particular row. We check the best cell in this particular row that corresponds to that 3. So that cell is this one of 2. And the one we are now assigning. So we check the row total and column total, 250 and 400. 250 is actually the smallest. So that means we assign 250 there, and we shall be done with column A or destination A. And this one shall be remaining now with 150 units, 150 more units to be assigned elsewhere. So we now begin again the second step of calculating the differences in column and the differences in row. But since we are done with destination A, we have said you put a dash. I think whoever had asked now is okay. Can proceed.
Yes.
Thank you.
Thank you.
Now let's begin now getting the column differences and row differences. Maybe we assign ourselves. Let's fill in, then before we confirm. 1 minute, let's calculate the row difference and column difference for that second set. So we agree the second set here will be 2. This will be 2. This will be 2. And here you should be talking of 1 and 4. So it's 3.
1, 1.
1,
1, 1, 1.
1, 1. Huh?
Yes.
Good. And the highest now is this particular value.
3.
And so that means we now begin, we identify the best cell in row 1, which is this. So that now, when I compare 300 and 350, 300 is the least. So I assign 300 here. So I'll have depleted source 1, but then you'll find that destination B will still be requiring 50 more units. Will still be requiring 50 more units. So I need to go to the next stage. So that means row 1 is not under consideration again. So it's a dash. Same to column 1. Here dashes. These others we need to calculate now the row and column difference. So we are just now talking of 6 minus 3 because they are 2. So that's 3. 5 minus 3 is 2. 9 minus 2 is 7. Then this side I'll be talking of 6 and 5. 1. 3 and 2. 1. We are together up to that stage.
Yes. Yes, Mali.
All right, that's okay. Now we can now. So at this stage now you can see the 7 is the highest, right? 7 is the highest. So that means now 7 corresponds now to 7 corresponds to this particular column D. So that is the one we need to first we need to assign, but we assign only the best cell in that particular column. The best cell in this particular column between 9 and 2 is this of 2. And so 2 here, I'm checking 200 against 500. The least is 200. So I'll have now met the demand of destination D. But then this one will be remaining with 300 more units. They assigned elsewhere. So that means the next row and column difference, this will be dashes. Now I begin now here, 6 and 3 is 2. I mean 3. Then 5 and 3 is 2. Then I have 6, 5, 1, 3, 3, 0. So I now come to this as the highest. Highest is that. And so I first of all assign, I'm just using different colors for people maybe to see clearly what you're doing. So I begin now again assigning this particular column. The best cell in that column is this cell of 3. So I'll be comparing 50 against 300. So 50 will come here. And so I'll have now met the demand of destination B. But then source 3 will still be having 250 more units to go. 250 more units to go. So you see now you cannot now begin row difference, column difference because you now have like just one. Because you see now you have just 2 cells here. And these 2 cells, you can see this 150 units in this particular source 2. You see, they cannot come down here. They just have to come here within the same row. And these 3 units, this 250 units, they just have to come here. So 150 and 250 gives you 400. Huh? So that's how you do now the assignment, so that you now pick up whatever you have assigned. 300 times 1 plus 250 times 2 plus 5 times 150 plus 50 times 3 plus 250 times 3 plus 200 times 2. So that's what we sum to give us the basic initial feasible solution. So if we sum that, gives us what?
We did 50.
50, yeah?
Yes. Yes.
Thank you, thank you. So I think that's what I also got from my end, so that's fine. So I said VAM method has some, is a bit special when I was mentioning among the methods of determining the basic feasible solution on this particular slide. Yeah, so with VAM method, one thing I'll say is that, yes, it gives us the basic initial feasible solution, but the value it gives us is actually optimal again at the same time. So why I'm saying this is sometimes when you ask students just to determine, maybe to optimize the problem, they just begin with the VAM, because once you have done VAM, whatever you get is the optimal. There's no way you'll get a value that is better than what you have or smaller in terms of cost of transporting. Yeah? But these other ones can give us higher value that may require again optimizing. But it's very important to know all these techniques, because some of the techniques of optimization are more involving than maybe the VAM method itself. So whenever we ask questions, we are always specific even on which technique to use. So that if we want student to optimize, if we want the student to use VAM method, we shall always tell the student to use VAM. If we want the student to use modified, we shall always be specific. And so it is good to know all of them so that you see the difference. So ladies and gentlemen, I want us to stop there today. Today was just looking at how we can determine the initial basic feasible solution, which we have said is the first phase of solving a transportation problem. So that maybe from next time we can now look at how do we now optimize the initial basic feasible solution we have used by looking at the various techniques that are even proposed on the course outline. I don't know whether you have any questions so far.